Hello everyone, welcome back to OLMJEE. So I am back with another series which is Olympiad questions which are relevant for JEE. And thanks for the good response on the previous NACP videos, and I'll be uploading more NACP PYQs of I'm currently working on the electrostatic and laws of motion PYQs of NACP. And let me know if this Olympiad series was also very helpful for you, so I will continue this series also. So today we have a question from the European Physics Olympiad, which says that one end of a thread is tied into a loop of length 2 pi r, and a cylinder of radius r is put through the loop. The coefficient of friction between the thread and the cylinder is mu. The free end of the thread is being pulled parallel to the axis of the cylinder. So this free end is being pulled parallel to the axis, and the force is represented by this arrow. And while this is being pulled, the cylinder is at rest, so the cylinder does not move. So if the length of the loop is longer than the critical value L0, the loop can slide along the cylinder without changing its shape. Otherwise, the friction locks it into a place, and increasing the pulling force would eventually break the thread. So if the length of this thread is longer than a certain value L0, then it will not be like this shape. It will just start moving downward in circular shape only. And if the length is less than that critical value or equal to, then it will form this shape. So find the critical value L0, and the weight of the thread is to be neglected, and thread will not twist when being pulled. And we are also given some formulae and approximations here. So let's begin with the solution. So first you are given with certain diagrams which show the situation of the question in different views. So this is the general view which shows the thread on the cylinder, and it is forming some parabolic shape. And this is the side view. If we view from here, if the observer is somewhere here and the observer is viewing in this direction, so he will see the side view. And then if we along this AB, if we cut this cylinder and then we unfold it, so this side will, the side which is behind this visible side will come this side, and it will look something like this. And this is the top view of the cylinder, and it is appearing to be circular shape. So now this, we are analyzing a small section of this thread which has horizontal length delta x. Okay, and the section is this section, and the forces on it are shown by the arrows. So if this is tension in this direction, so this will be Tx and this will be Ty. I'm breaking the tension into two directions and assume this has to be T dash, because we don't know if this T and this T dash are same. And this Tx dash will be here and Ty dash will be here. Friction is acting upwards because this thread is being pulled downwards, and a normal force is acting perpendicular to the surface of the cylinder. So now, since we are asked the maximum value of this length for which it will not slide, so we know that if we are asked the critical value of this length, then we need to consider the maximum frictional force acting on it, because if less frictional force is acting, then more force can be applied before it starts sliding or it breaks. So we are asked the critical length for which string does not break slash slide. Hence we need to consider maximum frictional force. maximum slash limiting friction. Hence, the symbol of friction is delta F, because all these forces will be are acting on this very small element. So we are taking as delta F and delta N. So delta F will be equal to mu into delta N, which is the limiting force. We know this from laws of motion. So this is the first equation that we found out. Okay. Now, since this thread is not moving, it means that the thread is in equilibrium. So we will write the equilibrium equation in different directions. So first we will write in x-axis. So this I had assumed as t dash. So this will be tx dash and this will be ty dash. And this I had assumed as t. So this will be tx and this will be ty. So now we can see that in the x direction only tx and tx dash are acting. So this means that tx minus of tx dash must be equal to 0, which gives us tx is equal to tx dash. So this gives us that the component of the tension in x direction will be constant. And this is a very well-known fact in catenary problems. Catenary problems you can find on YouTube or in Pathfinder and different Olympiads. So in catenary problems, always the component of the tension in x direction is equal, because there is no other force in the x direction. So now we move to the top view and we relate the tension and the normal, because normal force is not given and tension is also not given, but if we relate them, then we will have one less variable. So now first I need to prove something. If we see the whole length of the circle, which is the circumference, so the circumference has the formula 2 pi multiplied by r. 2 pi is basically the angle which needs to be covered to cover this whole length. So similarly, by kind of a unit 3 method, we can write this was given as delta x, right? This was given as delta x here. Let me make this more clear. This, if we are taking this as x, the component we are analyzing starts at x and the length of the component in horizontal direction is delta x. And this is the horizontal direction only. This is not the actual length. This is the horizontal length that we will see from the top view. So this will be equal to the angle which needs to be covered to cover delta x is delta phi, we are assuming. So we get this equation. Now we need to relate the normal and tension. We have done this in questions where there is friction on the pulley also. So we do something similar here. Let me magnify this triangle. So the tensions will be acting perpendicular to this side. This is because the Tx is tangent to this cylinder, right? So it will be making 90-degree with the radius, because tangent makes is perpendicular to the normal which passes through the center. And this whole angle was delta phi, so this small angle will be delta phi by 2, right? So by alternate angles, this angle will also be equal to delta phi by 2, and this whole angle was 90 degrees, so this angle will become phi by 2 minus delta phi by 2, So the component of Tx in this direction will become Tx cos of pi by 2 minus delta phi by 2, which is equal to Tx sine delta phi by 2. And similarly in this direction also there will be Tx sine delta phi by 2, and normal was acting this way. So the equilibrium in radial direction we can write this as 2Tx sine delta phi by 2 is equal to normal. And since this delta x is very small length which we are analyzing, so from here we will find out that delta phi is delta x by r, which is even smaller than delta x. So delta phi is very small angle, and delta phi by 2 is even smaller than delta phi. So delta phi by 2 is a very small angle, and we know that if the we take the sine of the very small angle, then it can be approximated to that angle. So this will become 2Tx delta phi by 2 normal is approximately equal to this, and from here we can substitute delta phi, so it will come out as Tx, as cancelled 2, so it will come out as Tx multiplied by delta x by r. So this is the third equation that we obtained, right? So the first equation was finding the maximum limiting, proving that the friction will be limiting friction. Second was that the horizontal component of tension will remain constant. And third, we analyzed the equilibrium in radial direction and found a relation between normal and the Tx. Now we are moving to the third equilibrium equation, which is equilibrium in z direction. So this was T dash, this is Tx dash, this is Ty dash, and this was T, this was Tx, oh sorry, this was Ty, and this was Tx. So now in z direction there is one more force, delta f, and normal is acting perpendicular to this plane, so that is delta m. So in z direction we can see that it will be, since this is the positive direction downward, so Ty minus of Ty dash minus of delta f is equal to 0. But Ty and Ty dash are not known, and there are two more variables that we are introducing, so I am not too keen on introducing these two variables. And since we have already proved that Tx dash and Tx were equal, so let me remove this apostrophe. So if we can represent this Ty dash and Ty in terms of Tx. Let me show you how. So this is T dash and this is Tx, right? Let me draw this a bit longer. And this is Ty dash, and assume this angle is theta. So if I move this Ty dash to here, because vectors can be moved, so tan theta is equal to Ty dash by Tx dash, right? Because this is forming a triangle, so this angle I had taken as theta, and this angle is also equal to theta. And we know that the angle from the positive x-axis can be given by the differential of this differential, which is tan theta is equal to dz by dx. The slope is given by this, right? Differentiating y and x, y in terms of x. So this will be equal to dz by dx. From here we will get ty dash is equal to tx dash multiplied by dz by dx, right? Similarly, we will get also this uh, the x coordinate of this point was x comma 0, and x coordinate of this point will be x plus delta x comma 0. Hope you understand this, because this is delta x and we took this element starting at a distance x from the origin. So this will be at x, and ty is equal to tx dot dy by dx at x plus delta x, right? So now this was the equation of equilibrium in the z direction. So now we can substitute. So it will become tx dot dy by dx at x plus delta x minus of tx dash, or should I say tx, because tx dash and tx are equal. Sorry, this was dz, not dy. At x minus of delta f. So delta f was mu into delta n, and delta n was tx delta x by r. So we can write this as mu into tx delta x divided by r is equal to 0. So from here we can cancel out tx, because this is common in all the three terms. And if we take this term to the right side and cross multiply by delta x, so this will become now. This term is a bit special because, let me remind you, we know also, since the delta x is very small, we can take the limit. Since we cannot divide by quantity that is approaching 0, so we will take limit delta x tends to 0. So we know that if we have limit delta x tends to 0, y at x plus delta x minus of y at x divided by delta x. So this is given by, this is the formula for the differential at x. So dy by dx, right? So using this, we can use this on the above equation. So it will become d square z by dx square is equal to mu by r, right? This is the differential equation for finding the trajectory of this thread. If we solve, we will get the trajectory, because we will relate the x component and z component of the thread. So we will get the trajectory, which is the shape of this equation for the shape of this thread. So this basically means that d by dx of dz by dx is equal to mu by r. So now we can integrate this. So this will become basically 1 multiplied by So we can integrate this as dz by dx is equal to mu r multiplied by x plus c1, and again we can take the dx on the other side, and then we can integrate this. So it will be z is equal to mu r multiplied by x square by 2 plus c1x plus c2. Okay, and now we need to remove the constants. So we need to find some constraints. That the origin is here, so that means that at x is equal to 0, z is also equal to 0, and the tangent makes an angle of 0 degrees with the x-axis, so tan theta will be 0. So the slope is 0, which gives us that z dash 0 is 0. So applying the constraints, we have so from here we will find out that 0 is equal to 0 plus 0 plus c2. So c2 is equal to 0, and first let us find out z differentiation of z in terms of x. So this will be plus c1, and we are given that this is equal to 0 is equal to 0 plus c1. So this gives us that c1 is also equal to 0, which finally gives us the equation for the shape, which is z is equal to mu into x square by 2r. So we can see that this relates the z and x components. So this is the trajectory of the thread, and since z varies as x square, this is the equation of a parabola. So this is a parabolic shape, and now we need to find the length of this thread, and we can use this trick to find the length. Assume this is the thread, and assume that if we integrate small parts over the entire length, then we will find the length of this thread. So let us take this at distance x from the origin, and this is at y above the x-axis, since this is in the positive direction. So this length will be dx, and this length will be dy. So this length can be given as dx square plus dy square, right? Using Pythagoras theorem. So if we integrate this square root, we will get the length, but right now we have two variables inside the integral, so we need to reduce this into one variable. So for that we can use this. If we take dx square common out of this square root, then this will become 1 plus dy by dx whole square multiplied by dx. And dy by dx we can find out from here. Sorry, this was z. I should take this as z. this was x, this was z, so this will be dx and this will be dz. So this length is given as dx square plus dz square, and then integrating this, here also dz, and dz by dx we can find from this equation, which will give us dz by dx is equal to mu x by r, right? So now we can substitute this here. So this will become 1 plus of mu x by r whole square, so multiplied by dx. And since we have reduced this to x variable, so we can put the limits now. So this is origin, and x coordinate of this is pi r, and x coordinate here is minus pi r, right? So we can put the limits now from minus pi r to pi r. Also we can see that the area on the area below the curve on the right side of the origin is exactly similar to the area present on the left side below the curve on the left side of the origin. So this can in turn be written as, changing the limits on the right side, this can be written as the area of the right side multiplied by 2, which is this. Now this kind of integral was given in the starting of the question, which is that 2 into integration of root 1 plus x squared dx is equal to x multiplied by root 1 plus x squared plus arc of this parabolic hyperbolic function. So this will become, if we let us substitute this as t, so if mu x by r is equal to t, then this will imply that dx is equal to r into dt by mu, and this upper limit will become mu into r by into multiplied by the upper limit. Sorry, this was pi r. So the upper limit will become pi mu. So now writing the new integral, we have and I am taking the r by mu outside. So we were given the formula for this equation as r by mu was not there, so this was t 1 plus t square plus r t, right? And now we can substitute the t. No, we can put the limits, which was 0 and pi mu, which will give us r by mu multiplied by pi mu 1 plus whole square plus arc of this. So now this will become this is the limiting line. So we have solved the question. Now we can also verify this as if we take a very small mu which is approaching to 0, then the thread should move down instantly without changing its shape. So the maximum length will be 2 pi r only, because it will start moving as soon as we pull it. So if we put mu as very small, then this limiting value should tend to 2 pi r, right? So we can prove that. L naught will become and this we were given as arc sine of sine hyperbolic function x is log of x plus 1 plus root 1 plus x. And since this value is very small because mu is approaching to 0, so this can be approximated to root 1, which is 1. So this will become r pi plus, and we know that this value can be approximated to 1 only by the same logic that we applied here. And we know that if x is very small, then this can be approximated to x. So this will also become, there was a r mu also, no? So this will become r by mu multiplied by pi mu by this formula, because x pi mu, which is x, is very small and this is 1. So this is of this form, and I'm approximating it to x, which is pi mu. So this will finally give us 2 pi r, which is in accordance with our intuition. So we have finally solved the question, and this was a very good question. And this can be thought of as a combination of catenary problems plus problems where we have friction on the pulley and we do normal and friction analysis. And you can find many such problems in Pathfinder also, but this is a problem from European Olympiad, and this is a very good problem for clarifying concepts. So don't forget to like and subscribe and comment if you found this helpful.